my great pleasure today to welcome Felix Kurz for this 70 MRI seminars. So Felix Kurz was from Heidelberg in Germany. So he was head of clinical 70 MRI at the German Research Cancer Center, and he's expert in quantitative MRI imaging. And from January, he's now in University Hospital of Geneva as head of diagnostic of neuroradiology unit. So Felix today will talk about structural and functional oncology imaging at ultra high field and the current challenge. So thank you, Felix, to give this presentation and to accept to give this talk a bit last minute.
Thank you very much for this introduction. I hope you can hear me well, as I have the tendency to speak a bit low, but please tell me if it's too silent. So, okay, sorry. Okay. So, I just wanted to present some of the results that we did, my group and other groups in Heidelberg in the last years. And to motivate, I wanted to show this slide by Felix Tobias, who's also from Heidelberg, who could show about 10 years ago that when you have IDH mutated glioma, which is a kind of lower grade brain tumor, in this case it was a grade 3 tumor, that rows you only see in MRIs usually this part of the tumor, whereas in fact there are multiple cells already on the other side of the brain, also in the corpus callosum, and everywhere where you see black dots, basically there are tumor cells, and they found this in histological studies. So of course it's interesting to see where these tumor cell nests are, and if you can find specific biomarkers to track them and quantify them. For the case of diffuse gliomas, the molecular pathogenesis is still not completely understood, and it was found that there are usually nests of resistance of these tumor cells, preferably in the white matter. So when you, for example, resect the tumor completely, then it's basically just a question of time when, starting from these cells of tumors in the white matter, you have a recurrence of the tumor. And on plus, you have an infiltrative growth that colonizes the whole brain. Just to clear maybe what we understand between structural and functional imaging, because there are a lot of people working on fMRI. In our case, we refer to functional imaging as anything that has a non-structural meaning, basically attributing a functional meaning, such as diffusion imaging, perfusion imaging, or also metabolic imaging, magnetic resonance spectroscopy that gives us information about specific tissue metabolites, but also oxygenation-based imaging and some other methods from nuclear medicine. So what are the advantages of ultra-high field? I'm sure that most of you are more or less familiar with this, but of course you have a much higher SNR that scales quadratically with the B0, so the magnetic field strength, and whereas the noise only scales linearly. So you have a significant gain in signal-to-noise ratio, giving you either a very high resolution or giving you the possibility to measure at a similar resolution to 3T, but in a shorter amount of time. And of course, you can do all kinds of other things in terms of functional imaging, based on an increased susceptibility difference at ultra-high field. So you see better T2-star associated structures, you can do better QSM and so on. And we will go further into this later. So what we've been working on, first of all, are correlative approaches. And when you look at these images, you see that in conventional MRI in clinical hospitals, we use 1.5 and 3Ts, and now the 7T, obviously, here in Geneva. But with these still high field, but less than ultra high field methods, we have resolution that goes usually down to 0.7 millimeters. 70, we can go even down to 100 micrometers if you measure ex vivo. And then for the rest, when you want to do a real ultrastructural exam, you have to rely on methods from microscopy, like multiphoton microscopy, histopathology, or synchrotron CT. And there are indirect methods explored currently by which we termed histological MRI, which uses intrinsic features of the signal decay that is related to microstructural properties such as cell size or vessel size or vessel density. So these are 7T images from the Heidelberg scanner that were recorded in 2012, I think. So at the time already you could do more or less good images. You see here in this glioblastoma on the left hemisphere very well the delineated vessels in this T2 star image, in part due to the increased deoxygenation of the tumor that is connected to the energy metabolism, but also to the angiogenesis of the growing tumor. And this, of course, looks even better at even higher field strengths, in this case, an experimental 9.4 Tesla machine, where we scan the mouth brain. Here you see the tumor in the left lower hemisphere, almost completely dark because of all the neovascularization. And this can also be proven histologically that you have mostly this effect due to the vessels and less due to necrosis, which is here. So in this MRI images, there's almost no, or at least much less signal than for the vasculature that is. And indeed, we can look at the vasculature. We did in this case a selective plane imaging microscopy, and in red you see all the skeletonized vessels in a healthy hemisphere, and in this case, in a tumor hemisphere. So you see the vasculature is very different, but it's mostly in this case due to the bulk growth of the tumor. So the cells grow, they displace vessels. Of course, there's also new angiogenesis, but in a lot of gliomas, you have more an infiltrative growth where you don't see so much of a difference in the vasculature. So this is a challenge. We try to go a bit a theoretical way in that we used this vasculature and we simulated the MR signal at 3D and 7T to characterize more vasculature and healthy vasculature. But this is a very idealized setting, so there are no other effects whatsoever. It's just basically the vasculature that we're looking at. But it can help to differentiate tumor voxels and healthy voxels. So basically, we created virtual voxels based on more or less arbitrary sizes that we chose inside this 3D vasculature volume. And as I said, we worked a lot on correlative approaches with, in this case, 9.4 Tesla MRI in an animal setting. And correlative means we do an MRI, mostly in vivo, but also ex vivo of mice and rats. And we connect these results with multiphoton microscopy, synchrotron CT, but also light sheet microscopy. And in this case, to give us a structural correlate of what we see in the MRI. And this has been done by a PhD student of mine, where we basically correlated the MRI image, in this case T2, but we also recorded T2 star, T2 maps, T star maps, and we superpositioned the vasculature from multiphoton microscopy. And you see here in green, like this. It's in green the tumor cells. So we have to run it again. Oh, it crashed. But you saw the tumor cells, I hope, and the idea was that these tumor cells, they give us an image signature. And of course, when we have all the other correlative maps, we can quantify this image signature. And we know where the tumor cells are, so we have a direct correlate. This is what's interesting for us. Oh, sorry, the program crashed. Then I restart. This gives us the opportunity to see the video again. Then we see in green, as I said, the tumor cells and the signature that we expect from the mapping sequences. So we have a quantitative correlate of the actual position of the tumor cells. So this may aid in radiomics and quantitative computational based methods. And we can follow up since these methods are in vivo. So the microscopy is done through a cranial window of the mice. So you can follow basically what's happening at day 60 or earlier or later. In this case, you see the tumor cells in green infiltrating more and more of the tissue. And you can, of course, then quantify all of this. We did the same for diffusion-based methods because we thought that tumor cell nests or resistant niches of tumor cells are mostly found in white matter, in this case, the corpus callosum. So we looked at DTI measures of the corpus callosum and we correlated with, in this case, 3D intravitreal microscopy, where you see here the infiltration of tumor. But in this case, we didn't find any meaningful signatures, which is a bit sad, considering that we have a very high resolution of, I think, 200 micrometers in this case, and we have no effect in diffusion, which is what we expected. But unfortunately, this doesn't give us more information about this. So challenges, when we translate to 70, I think are mostly well known. We have a decreased T2 time, which means in some cases longer scan times. We have a lot of radio frequency field uniformity, inhomogeneities, B1 and B0, and we have strong susceptibility effects that can lead to geometric distortions or intravoxel defacing. But we have a very strong chemical shift effect. This we can use for spectroscopy and CEST imaging. So, and of course we have a much higher SNR, so there are no pros to this, unfortunately. Just cons. And of course we can do ex-nuclear imaging. So I just wanted to show you some images from what we did ex vivo. So we used an ex vivo brain, post-mortem brain, and we put it in a kind of cylinder. We put agarose gel around it. And so when you see on this T1 image the air bubbles here, you can imagine how it looks like in an SWI image. So it's ultra distorted. So it's already for ex vivo imaging a huge challenge to get out all the air bubbles to make it like really homogeneous. But the second challenge is the B1 in homogeneity. That mostly arises due to the dielectric effects from standing waves, because the Balmer frequency at higher field strength, of course, is higher. So the wavelength gets shorter, and in this case, the wavelength reaches sizes that are comparable to a human head. So when we use a bird cage coil, like in this case, we start seeing these strong artifacts. So this is also something that we had to deal with. And so the images here at the 70 is already much better, which is good. And of course, we have problems in the suppression of fat and water. When you look at this peripheral nerve in the thigh, on the left you have a 3D image, and you see already not so bad, these slightly enlarged neuronal fibers here that are also pathological with an increased T2 signal. And here you have the corresponding 7T image. And you see, of course, the resolution is much better. You see much better the neural structures and also the hyperintensities, but surrounding it, you have a lot of artifacts because water and fat spectral lines at 7T are widening, and this makes it hard to produce good images. But still, you can manage using parallel imaging techniques, and you can compare 3T and 7T images at high field strength in this case, and you can get, or at least this gives the impression that you see much better also in normal nerve, peripheral nerve, the neural structures. So I think in this case it has very, very good advantages. And the images I saw here with the new generation of 7T are spectacular. So I really hope that we can see more of this. Going further, we also did experimental sequences. We basically constructed gradient echo sampling of skin echo, a so-called Jesse sequence that allows us to simultaneously measure T2, T2 prime, and T2 star by basically sampling over, by gradient echo sampling over the peak after the spin echo. And this gives us simultaneous information about the oxygen extraction fraction, but also the cerebral metabolic rate of oxygen consumption. And this is indispensable to study brain microstructural composition and function. And it only takes 6 minutes compared to 30 minutes for a very good T2 mapping. So when you look at these images on 3T, you see it works on 3T, actually not bad. But it's much better on 7T and still within the same time frame. So we expect that this might also be a step forward in quickly having functional mappings T2, T2 star, and respective quantitative information. We also did sodium imaging. I am myself not so much, but in the Heidelberg groups it's very popular, and of course, you know, X nuclei, they have resonance frequencies that are a bit lower than protons. So that means the wavelengths are a bit higher again at 7T. So you don't have these standing wave effects. You can use actually the birdcage coils, but you still suffer from low resolution, as I can show you here. So these are sodium imaging pictures of a higher grade brain tumor. And you see, especially here in the solid parts, you have an increased sodium uptake that is mostly related to the increased energy metabolism. So basically the sodium potassium ATPase shuts down in the cellular membrane, and the sodium accumulates intracellularly. And this can be measured, and you get an information of what's happening, but still the resolution is okay. But I think Siemens already has an FDA approved coil for sodium imaging at 7T, so maybe you can, or at least it was in the process of being approved. So hopefully we see some more of this, and then you can of course do quantitative analysis, and you see that, for example, here in necrotic or contrast enhancing tissue, you have increased sodium uptake. And you can even use it to differentiate between glioblastoma and non-glioblastoma tissue regarding the tumor grade. Furthermore, you can do a pH mapping based on 31 phosphorus isotope imaging. In this case, we use basically the increased spectroscopic information, where you can differentiate between an intracellular inorganic phosphate peak and phosphocreatine that one pH. And also here you see, when you do this based on this multi-voxel field, you can look at this higher grade brain tumor, see how it basically evolves under angiogenic therapy. So you see no real information here, but here later, a few weeks later, you see a progression, and inside the area that progresses, you have slightly increased pH value. In this case, can be used as a biomarker, but very experimental. But in my case, in my opinion, interesting. And there were also experiments done with 17O isotopes, which is stable and non-toxic. So people basically inhale 70% 17O gas, and then you can directly do imaging. Also with the temporal resolution, so you see how after oxygen inhalation, the signal goes up. Here for gray matter, it goes up a little bit less for white matter, and it goes up much less for the tumor volume. And when we think back to, 100 years ago, Warburg did this hypothesis that in tumor tissue you have a non-oxidative glycolysis that leads to lactic acid fermentation. It's basically visualization of the Warburg hypothesis that in tumor tissue you have mostly non-oxidative glycolization. This has been done also already, just 3 years ago, 4 years ago. And of course, there are spectroscopic methods and images from Andronese from Boston that in this case have been used for lower grade glioma, where you have IDH mutations, and these can lead to an excessive alpha-ketoglutarate production, which in turn leads to an increased amount of 2-hydroxyglutarate, 2-HT, and this basically accumulates in the tumor tissue. And when you do a full spectroscopic analysis, done here before radiation therapy and here after radiation therapy, you see that the 2-HG signal goes down, whereas all the other metabolites stay more or less the same. So this can be used or it is a metabolic hallmark of glioma growth, and can be used in this case for a spectroscopic quantification. And last but not least, we have a very big group that was doing CEST imaging in Heidelberg, and I'm not sure if you are familiar with this. It's chemical saturation, where basically it means that you have a chemical exchange between bound protons of mobile proteins and the water pool. Mostly it's done with amide photons, so NH. And when you do a pulse, you basically can excite this ensemble of protons, and you get a little dip here in the spectrum. And this lets you produce so-called CEST or Z spectrum when you divide by the normal water saturation peak, and you can quantify the signal of this magnetization transfer for APT or amide transfer. And then you can look, when you know that APT is basically connected to cell proliferation and higher cellularity, you can look at tumors and study them under therapy, like it has been done by Jiwon Park of Azam Hospital in Seoul. And in this case, we have more or less midline tumor that after angiogenic therapy showed a slight decrease in the APT signal, and further follow-up revealed actually no progression. Whereas here you had a good effect of angiogenic therapy, so a decrease of APT, and later on, unfortunately, a strong progression. And in this case, you have this was the tumor was. So basically here you have almost no APT signal, but after anti-angiogenic therapy, you see a slight increase in the signal. And this patient had a strong diffuse infiltrating growth afterwards. So this can be used to assess therapy response for anti-angiogenic therapy. And of course, there are newer techniques now. It's a more recent paper with relaxation-based APT CEST, where you can better delineate the APT signal. compared to the non-relaxation compensated cyst images. And here, for example, we have a tumor with a strong APT signal. And this also had a much worse outcome than the on the left. Okay, so just to give a quick summary or outlook, I think that correlative imaging to look for hidden microstructural signatures of tumor cells or vasculature in clinical and experimental MRI is very interesting and promising path to go. But of course, when you do correlative imaging, you have to often go back to tissue sampling, to ex vivo, and so on. And it's a very experimental setting. In an in vivo setting, it can be, it's not done yet in this case, unless you use spectroscopic methods. And I think with the 70 MRI functional imaging sequences that I presented, but also that are at hand, slowly this is all finding its way into clinical application and practice. And we have now, I think, worldwide 170 machines. So the last 1 or 2 years, with 20 new machines and now the new generations. So there's a lot of space for also larger clinical cohorts now, or multi-center studies that let us assess clinical benefit in structural and functional oncological imaging. So, and this is where I close. These are my collaborators in Heidelberg and outside, and I thank you for your attention.
Thank you very much, Felix, for this overview of position research on 7 Tesla.